These are the notes on acceleration. Accelerated motion is another name for acceleration. Now, acceleration happens when velocity is not a constant. When velocity changes one way or the other, you have acceleration. Now, in everyday language, we use the word decelerate as well as accelerate. So if we are, let's say, speeding up, going faster and faster and faster, then we are accelerating. But if we are slowing down, going slower and slower and slower, then we are decelerating. However, decelerating is actually just another form of acceleration, but you are accelerating in the opposite direction of your motion. Okay, so technically the term acceleration is applied either way, but I will use the word decelerate because it is something that you already probably have heard and will make sense to you, and they do use it in physics. Just realize that you can accelerate in either direction. The word accelerate has an interesting etymology, an interesting word origin. I love getting into where do words come from. And because I used to study Latin when I was in high school, I was at public school, but we just had Latin and I really liked it. Um, Accelerate comes from a mythological character, a character that may or may not have ever lived, and nobody's sure about this. There's a story about the founding of Rome, and that might have been completely made up. Like, oh, it's called Rome, so there must have been a guy named Romulus. And let's see, he had a twin brother, Remus, Romulus and Remus. And they were raised by wolves. Okay, really? So this story gets extremely iffy because it doesn't seem plausible that two twins abandoned in the hills would be raised by wolves, etc., and come back to be these like almost like superhero type characters. But anyway, the story is that Romulus sort of won out most of the time. Romulus saw the most crows when he was counting the crows and got to found the city of Rome between the seven hills, which led to the Roman Empire and all that. And it was named after him. Otherwise, we'd have a city called Rheims, I guess, if it was named after his twin brother. So his twin brother often lost out, and the way he lost out the most was unfortunately the way that he died. He was mocking his brother's brand new city, and he jumped over the wall, and they thought he was an invader. And then Romulus's friend Celer, that's how you pronounce it, C-E-L-E-R, killed Remus. Then he realized who it was. He realized, oh my gosh, I just killed the first king of Rome's brother. I better get out of here. And I guess Celer was very athletic, and he ran really fast. So fast that the word accelerate was named after him. And celerity is a word that we don't use as much, which means swiftness, being very fast. Even the letter C, look at the bottom, E equals mc squared. That letter C stands for celeritas in Latin, or celeritas, some people would say, which comes from his name, Celer. Some people would pronounce his name Celer, but actually in Latin, the C was always pronounced as if it were a K sound. So his name was Celer, okay, but now we would say that in English we might say Celer, and then we put that in accelerate and celerity. So it's just interesting to see where these words come from. I find it fascinating, and nobody's sure if that guy ever lived or if he was a made-up guy in a mythological story to make Rome seem more special and important. Probably a little bit of both are true. So you can move smoothly, that is called uniform motion. Uniform motion we actually don't even feel. Uniform motion is funny because if you're moving uniformly, you don't even feel it. You don't believe me? Well, guess what? Right now, even if you're sitting in a chair, perfectly still, you are moving. Isn't the Earth spinning? Yes, the Earth is spinning very fast. At our latitude, the Earth is spinning at over 1,000 kilometers per hour, over 700 miles per hour to the east. Do you feel that? The Earth is moving around the sun at over 50,000 kilometers per hour. You don't feel that? The solar system is moving All of those are uniform motions, and we don't feel them. So that kind of shows you that we don't notice uniform motion. If you're in a car, let's say, and you're not driving, let's say you're in a passenger seat, someone's driving you in a car, and you're moving on a very smooth road, and you're going at a constant velocity. Let's say you were to close your eyes, not if you're driving, of course. You should not feel the motion. There should be nothing about the way you are moving that tells you that you're moving, unless you hit bumps in the road. You might notice the bumps and then realize, oh, I must be moving. Okay? So when you're in uniform motion, you don't feel any pushes or pulls. Okay? But when you are in non-uniform motion, it does feel like you are being pushed or pulled. If you're in non-uniform motion, okay, let's say going faster and faster forward, it feels like something is pushing on you, pushing you backward, so to speak. Let's say you're in a car accelerating forward, you feel something pushing you. And when you make turns, you feel like you're being pushed to the side, okay? So again, it says at the bottom, if you're in uniform motion, your eyes are closed, you shouldn't feel like you're moving. Like right now, let's say you're in a safe spot in a chair, close your eyes, doesn't feel like you're moving, but again, you are. Earth is spinning, among other things. The Earth is spinning very rapidly. Let's just stick to that one. And going up an escalator, as this man is in the image, is uniform motion. You're just moving up at the same velocity. So once you get on that escalator, once you've stepped onto it and begin moving, you remain moving at the same velocity all the way until the point where you're about to step off. So for that entire length of the escalator, okay, you are under uniform motion. That's a really good example. Now here we see 4 examples of different kinds of motion. Now, in physics, to simplify things, we very, very frequently consider things to be particles, like little spheres. Of course, many things are not spheres. The human body is very far from a sphere, but we like to consider a point in the middle of the body to be that object. It's much easier than representing, because look at how the hands are moving, how your head is swaying, your feet are moving. It gets really, really complicated. It's much, much easier to consider the center of mass, usually it's near the center of an object, as a particle. Okay, and that's often how we do it in physics. There's a very famous physics joke, I guess I'm giving you too many jokes, where they say, consider a spherical cow, right? Because in physics they make everything into a sphere for simplicity, even when it's very far from a sphere like a cow. Anyway, so we've got a person in A that's about to move, not moving, okay? Then we've got a person in B that is moving at a constant velocity. Now notice they were already moving when this sequence began, and they're still moving at the end, okay? They're evenly spaced out, assuming that these pictures were taken at equal intervals, like either every second, or every minute, that would be very slow. Every hour, that would be extremely slow. Every year, it just has to be the same interval, okay? And then in C, what do we see? We see the person moving, but wait a second, they're not evenly spaced. The spacing is getting larger and larger and larger. Oh, that person is speeding up. So they start off moving at the beginning, and then they move faster in the next interval, faster in the next interval, and faster in the next interval. So there is a change in velocity. They are accelerating, okay? And then in picture D, we see a person also changing their velocity, but there's a big space in the first interval. The space is actually less in the next interval, and less and less. So they are also accelerating. You might say they're decelerating because the direction of the acceleration is actually negative compared to the direction the person is moving. But that is still a form of acceleration. And if you want to call it deceleration, that's fine. Just realize that both of them are accelerations. One of them is positive and one of them is negative. And then what about in B? What was the acceleration? Well, the acceleration there would be 0 because the velocity is not changing. And what's the acceleration of the person in A? What is the acceleration if you're in one position the whole time? Let's assume that subsequent pictures were taken and the person remained in the same spot. So again, the acceleration would be 0. But then again, your velocity is also 0. It remains 0. Now remember that velocity is a vector, VV, right? So there's two ways to tell when something is accelerating on a motion diagram. One is you can just see, well, there's different spaces between the positions as long as we have equal intervals in between, different spacing, that should give it away. Or if you draw the velocity vectors, those arrows, which you could draw as the length between the spaces, you could notice that those are changing length. Now that is actually a better way of looking at it, because you can do more with those vectors than you can do with simply the spacing between the dots. Although you could sort of say they're very related, they're essentially the same thing. Those velocity vectors can be used to determine the acceleration. So notice that in both the diagram on the left and the diagram on the right, the spacing between the dots is changing. So you know there's some kind of acceleration. And if you draw in the vectors, which would be arrows that are pointing in the direction you're moving, that are the length of the space between the dots, you will notice that those are also changing. So when an object is speeding up, when acceleration is positive, you get longer and longer arrows as you move to the right. The arrows are getting longer and longer, every subsequent arrow. If the acceleration is negative, okay, then what you see is the arrows are shrinking in size. They're getting shorter and shorter with each subsequent interval. So the rate at which an object's velocity changes is called the acceleration of the object. When the velocity of an object changes at a constant rate, well, then it has a constant acceleration. Those are the easiest ones to deal with. Just like constant velocities were much easier to deal with than now we're seeing changing velocities. This is going to be a little trickier. So constant acceleration is the one we're going to deal with for the most part. So the average acceleration of an object is the change in velocity during some measurable time period, time interval, divided by the amount of time, the time interval. So because velocity is often in meters per second, and we're dividing by a time interval, which is also probably going to be seconds, we're dividing meters per second by seconds. So what we wind up getting as our unit is meters per second squared. Or you could say meters per second, but that sounds kind of strange. That is the way we measure acceleration. So it is a strange unit, and you got to get used to it. And just realize when you see meters per second squared, well, that must be an acceleration. Now, the change in velocity at a given instant is called the instantaneous acceleration, and that could be all over the place, just like your instantaneous velocity could be all over the place. So what we usually will be talking about is average acceleration. If I just say acceleration, I'm going to be talking about the average acceleration. So instantaneous acceleration can be taken from a velocity versus time graph as the tangent to the curve at any given point. So notice that that can vary wildly from any given moment. The object, if you take a tangent to the line, the slope of that would give you your instantaneous acceleration. Now, it's interesting to note how this changes, but for the most part, we will be using constant accelerations. This is the formula for acceleration. Actually, this is actually average acceleration, but this is the one we will be using, okay? So acceleration, A, equals the change in velocity. You should know by now that that delta, that triangle, means change, divided by the change in time, or the time interval, okay? So if you're changing velocity, if you're going faster and faster, that'll give you a positive acceleration, okay? If you're changing velocity, if you're going slower and slower, that will give you a negative acceleration. So just like displacements can be negative, velocities can be negative, and accelerations can also be negative. Time cannot be negative. Time has an arrow, it always moves forward. We're always moving it 1 second per second into the future, 1 minute per minute into the future, 1 hour per hour into the future. So time has its own arrow. Time is the only one of these things that cannot be negative. So just like we saw before, your delta x equals xf minus xi, final minus initial. Your delta v equals vf minus vi. It's a very similar pattern. And your delta t equals tf minus ti. So this is the pattern we always see. Final minus initial. Just don't do it backwards or you might get negative values when they should be positive and vice versa. Okay, so we take the one where we end minus the one where we began. Final minus initial. And that's what we mean by the deltas, by the change in position, the change in velocity, the change in time. Now why are we representing position with x? Because we're considering things moving along the x-axis. So similar to the way that we calculate velocity, we could either put delta v over delta t for acceleration, or we could substitute delta v for the way that we calculate delta v. We could substitute delta t for the way that we calculate delta t. So here's the longer form of the acceleration equation. And if you want to put the values in, if you prefer doing it this way, again, this is fine. Just do the order of operations correctly, and you will find out your acceleration. Please be very careful with positives and negatives, because that makes a huge difference, of course, with anything, but especially with velocities and accelerations. Please be very careful about your negative values. If you don't put a negative, we assume that it's a positive. So acceleration is a vector. Why is it a vector? Because it comes out of velocity, which was a vector. Why is velocity a vector? Because it comes out of displacement, which is a vector. So acceleration has to indicate the direction, positive or negative, based on your frame of reference. Okay, a lot of times, if it's not given, we assume that things are moving to the right if we're doing a graph, or we're moving forward. Like let's say it's a car, we're talking about positive if it's moving in the direction it's facing, and negative if it's moving backward. If it's a person, the direction their, let's say, nose is pointing is positive, and then behind their head would be negative. That's usually the assumption. And sometimes it'll be stated, sometimes maybe I'll forget to mention that. One simple way to determine average acceleration is by looking at two consecutive velocity vectors. In other words, the arrow you can draw between 2 points on a motion diagram, which would be your velocity vector, and then the one immediately following it in the subsequent interval, which often we choose 1 second as our interval. It isn't always our interval, but very frequently. So this is easiest when you do use 1 second intervals, because I can find the difference between those two velocity vectors. There's two ways of doing it. There's the simple way I'm about to show you, and then there's the proper way. So let me show you the simple way first, because this, as long as you keep it straight in your mind, this one works. You can see that they're both moving to the right. Okay, so let's call that a positive value. Well, now if I take one of my vectors and put it alongside the other, put them next to each other, then I can see one is longer than the other. It's the difference between them that is my acceleration, okay, or at least that's my delta v, let's say. So if I go from the head of the shorter arrow to the head of the longer arrow, at least in a parallel, you can sort of think of that as your acceleration. The only thing is technically that's your delta v, that's your change in velocity. But if that interval was 1 second, if that was 1 second later, if you divide it by a delta t that is 1 second, okay, then what you will have is your acceleration. So this is the way a lot of people think about acceleration, as being how much the velocity has changed in subsequent intervals. Now the proper way to do that is just slightly different. Notice that in the proper way to do it, you do line up the vectors, but one of the vectors, the initial vector, the one that is for the earlier interval, is reversed. Okay, so technically that is the way you're supposed to do it, but it amounts to the same thing. You're looking at the difference between them, and it still points in the direction of whichever arrow is longer, whichever magnitude is greater. That's the direction of the acceleration. So it's velocity final minus velocity initial, of course. So because it's subtracted, you're supposed to reverse the vector. I find that sometimes this can lead to confusion, but if you prefer to do it this way, that's fine. Just realize you can tell which way the acceleration should be pointing by whether the final velocity is longer or the initial velocity is longer. If the final velocity vector is longer, the VF is longer, then acceleration will be to the right in the same direction as the VF. If VI is actually longer, well then your acceleration will be in the opposite direction of VF, okay, to the left. To show you what acceleration looks like on a position versus time graph or on a velocity versus time graph, I'm going to show it on both. We'll see a moving object and its position over time. Now let's say for the first 5 seconds, we see it traveling like this. You see both of them plotting at once, and then we get to that position. So that is a steady slope. That is a constant velocity. And notice on the velocity versus time graph, you see the velocity is flatlining. It's 0.5 meters per second. But now let's say suddenly from that point on, we go at a different velocity. Notice that is not the same slope. Is that going faster or slower? Well, you can tell by the steepness of the slope how fast it's traveling, its velocity. So that's steeper, so it's going faster in the same direction. So notice on the velocity versus time curve, right at 5 seconds, it suddenly jumps up. There's an instantaneous change, and now the new velocity is 1 meter per second. So there has been an acceleration from 0.5 meters per second to 1 meter per second. And that's happened between second 4 and second 6. So if you looked at the vector from 4 to 5 and from 5 to 6, you could find the change in them, and it's 0.5 meters per second. And then you would divide that by the change, which is 1 second. And so it would be 0.5 meters per second squared. And that would be the acceleration over that short interval where it's happening there. So I wanted to show you all three at once. So let's see here. Same graph. Now you can see that in this case, the velocity is constant. So that means there's no acceleration. But then right at the end, notice it's going up there. We're going to have a little blip of acceleration. And that's when it changes to the higher velocity. So we do require some sort of acceleration to change velocities. If velocity changes, you need some kind of acceleration. Sure, I'm representing it there with that little blip at 4 seconds where the acceleration just momentarily jumps up enough to change the velocity, and then it drops back down to 0. So notice when velocity is flatlining, then you do not see any acceleration. Sort of like if position is flatlining, you don't see any velocity. If you're staying in the same place, well, there's no velocity. And if you're staying at the same velocity, there's no acceleration. So notice how these graphs relate to one another. You could take the derivative of one to get to the other. If you take the derivative of the position, well, then you get the velocity. The derivative of the velocity will get you to the acceleration. And you could integrate to go the other way back. So this is the same concept for finding the displacement on a velocity versus time graph. This is a bootleg integration. If you take the area under the curve or under the graph. So if you want to know how much displacement there has been over 2 seconds, you find the total area up until the 2-second line under that graph. And that will wind up giving you the displacement, because you would be multiplying the velocity, which is meters per second, times the time, which is seconds. The seconds would cancel out, and what you'd be left with is just the meters. So again, here you can see that this is one that's easy to do in our heads. So if we're going from 1 second to 3 seconds, okay, that's a change of 2 seconds. And if we notice, the velocity has gone from 0 to 8. So 8 minus 0 is 8 meters per second. So if we multiply 8 meters per second times 2, we get 16 meters because the seconds cancel. So we know that between second 1 and second 3, there has been a displacement of 16 meters. So this is like integration. This is going the other way, going back and reconstructing the earlier diagram. So you can do it either way. You could tell by the slope of the line to get the derivative, and that will give you the velocity from the displacement, and it'll give you the acceleration from the velocity. Or you could do it the other way around, find the area under the curves, which is really like integrating, and that will get you to move from acceleration back to velocity, or from velocity back to displacement. So if that doesn't make any sense to you, it's not the end of the world. It's just a way of understanding how these relate to one another. So the more you know about calculus, the easier it is to see this relationship. Here we have 3 graphs: position versus time, velocity versus time, and acceleration versus time for the same moving object. So we've chosen to start at position equals 0 meters, time equals 0. That's always easiest. Now watch what happens with this one. We see that, okay, it's moving, the position is changing, but it's actually going faster and faster. It's not a steady slope. So what we're seeing is a change in velocity over time. Okay, so velocity now has a slope to it. It's not a constant velocity, which would be a flat line velocity. Velocity has a slope. So what do you think the acceleration is going to look like of that? Think about it. If your velocity is changing at a constant rate, well, that's going to be a positive acceleration because of the way we've defined our terms. But the acceleration is now flatlining because you're accelerating the whole time. It's not at 0 there, it's just a low value. It's staying at a constant acceleration. So this is what a constant acceleration looks like. It's kind of like a parabola. It's almost exactly like a parabola. You go faster and faster and faster, so your position follows a parabolic trajectory. Your velocity is increasing at a steady rate, a steady sloped line, and then your acceleration is remaining constant, flatlining. So let's look at those all at once. Watch them all forming together. Remember, these are happening simultaneously, so it's good to try to think of them as happening together. Okay? The position versus time, the velocity versus time, and the acceleration versus time. And you could construct one of the graphs from the other. Each one is interrelated. Okay? It's just easier to see what's going on if you can see all 3 of them. So here we see another pair of position versus time graphs for the same moving object. And let's just see what's happening here. Okay. Well, the object begins at 0, that's good. And it goes, okay, it's going faster and faster between 0 and 3 seconds. So notice that that means the velocity is increasing. It's kind of like the beginning of a parabola right there, right? So that means our velocity is changing. The object is moving, but it's moving faster and faster. That means the velocity is increasing between 0 and 3 seconds. Okay, let's see what happens next. Okay, so between 3 and 7 seconds, what we see is the object is still moving, but it's moving at a steady rate. The slope is a straight line. It's a constant slope. That means the velocity is staying the same. So velocity isn't changing, it's flatlining. So notice that even though we did have an acceleration for the first 3 seconds, there must have been an acceleration there, so the velocity could increase, the acceleration stops. So from 3 to 7 seconds, acceleration would drop to 0. So I did not do the acceleration graph for this one, but we would see an acceleration between 0 and 3 seconds. We would see a positive acceleration. Then it would drop down to 0, okay, at 3 seconds, and it would stay there all the way until 7. Let's see what happens after that. After 7 seconds, now what we see is it is continuing to move, the object is moving, but it's not moving faster and faster, it's moving slower and slower, appearing to eventually stop, possibly. You'd have to see what happens after this, but it appears to essentially stop at 7 meters at that position. So what's happening there? Well, the velocity is now decreasing. The velocity is getting lower and lower and dropping to 0 by the time we get to 10 seconds. So what would that mean in terms of acceleration? Well, now what that would mean for acceleration, can you imagine? It means that the acceleration is actually negative. That would be a negative acceleration. You can have negative accelerations, right? Because notice that the slope between 7 and 10 on the velocity versus time curve is a negative slope. And so a negative slope would give me a negative acceleration, okay? So now to get the acceleration, we would take the change in velocity over a given interval of time, and I did not do that graph. So just keep in mind what you would see on that graph is a positive acceleration between 0 and 3 seconds, dropping to 0 between 3 and 7 seconds, and then going negative by the same amount that it was positive, you'd have a negative acceleration between 7 and 10 seconds. And that would, of course, be meters per second squared as my unit. Well, I wasn't going to make the acceleration graph, but then I decided just saying it in words might not be clear enough, so I made one. So now notice this is going to be the same velocity versus time graph that we had on the previous one. And now, next to that, we've got an acceleration versus time graph. However, pay attention to where the 0 is. The units of acceleration are meters per second squared. Look where the 0 is. It's way up high in the middle. That's to leave room for negative values. So let's look at the velocity for the first several seconds. Velocity for the first 3 seconds is increasing. Well, that's positive acceleration. So notice that the acceleration is above 0. Then after that, suddenly it drops, okay? The velocity remains the same for the next 4 seconds. That means the acceleration is actually 0. Notice that that is the 0 line. Even though it's way up there, that means 0 acceleration. And then finally, for the remaining 3 seconds from 7 to 10, we actually have a negative acceleration because the velocity is decreasing. So we are decelerating or accelerating in the opposite direction that we're traveling. We call that a negative acceleration. So I just wanted to make sure that you could visualize. It looks like a bunch of steps going down. But please pay attention to where the 0 is there. 0 acceleration is when you have a constant velocity. Like notice where the velocity is flatlining, that means acceleration is 0. So maybe now you can picture this better. I thought it was better to show you than to just describe it in words. That is the end of the notes on acceleration.